In this example, we are asked to write the full and condensed electron configurations and partial orbital diagrams for each of the following elements. We'll start with potassium. The strategy here is first to look up the element in the periodic table, then to write the full and condensed electron configurations, and then 3, to use this to write the partial orbital diagram. So starting with potassium, we see that potassium is atomic number 19 in the periodic table, and therefore potassium will have 19 protons and 19 electrons. Now we can write the electron configuration for potassium by starting at the top of the periodic table. We just go down to potassium, so the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And this is the correct electron configuration for potassium. In order to write the condensed electron configuration, we can recognize that the nearest noble gas to potassium is argon, and argon has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. And so for the condensed electron configuration, we can simply write argon 4s1, where 4s1 represents the highest energy orbital. Now we can check our work. As we said previously, potassium should have 19 electrons, and therefore we have 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, 6 electrons in the 2p atomic orbitals, 2 electrons in the 3s atomic orbital, 6 electrons in the 3p atomic orbitals, and 1 electron in the 4s atomic orbital, which gives us a total of 19 electrons. So our answer should be correct. Next, we're asked to write the partial orbital diagram for potassium, and looking at the highest energy orbital, we see that it's the 4s atomic orbital, and we have 1 electron in the 4s atomic orbital, so we should write our partial orbital diagram as 1 electron, which we write as an arrow pointing in the up direction, so it has spin plus a half in the 4s atomic orbital. And so this is the partial orbital diagram for potassium. Next, we're asked to write the electron configuration for carbon, which is atomic number 6 in the periodic table. And therefore we know that carbon has 6 protons and 6 electrons. And so we can write the electron configuration again by looking at the periodic table. The electron configuration for carbon should be 1s2, 2s2, 2p2, as shown here. In order to write the condensed electron configuration, all we have to do is recognize the fact that this part of the electron configuration, 1s2, represents the electron configuration for helium, which is the nearest noble gas. And so we can write the condensed electron configuration as helium 2s2, 2p2, where 2s2 and 2p2 are the highest energy orbitals. Now, checking our work, we know that we have 6 electrons in carbon. Looking at the electron configuration, we see that we have 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, and 2 electrons in the 2p atomic orbitals. And so, adding them together gives us 2 plus 2 plus 2 equals 6 electrons as expected. For the last part of the question, we're asked to write the partial orbital diagram for carbon. And for the partial orbital diagram, we're only interested in the highest energy orbitals, so the 2s and 2p atomic orbitals. And what this tells us is that we have 2 electrons in the 2s atomic orbital, and we have 2 electrons in the 2p atomic orbitals. And so, filling in our partial orbital diagram from lowest energy to highest energy, we always start with the s orbital because it's lower in energy than the p orbital. So the first electron goes into the lowest energy orbital, which is the 2s atomic orbital, and we place that electron in the spin up or spin plus 1/2 position. The second electron in the 2s atomic orbital gets placed in the spin down or spin minus 1/2 position, and this is due to the Pauli exclusion principle, which tells us that no 2 electrons can have exactly the same set of quantum numbers. And so if one electron is a spin up, the other electron has to be spin down. Next, moving to the 2p atomic orbitals, we know that we have 2 electrons in the 2p atomic orbitals, and the first electron we place in the first box in the spin up or spin plus 1/2 position, and the second 2p electron we place in the next 2p atomic orbital, also in the spin up or spin plus 1/2 position. And this completes the partial orbital diagram for carbon. Next, we're asked to write the electron configuration for sulfur, which is atomic number 16 in the periodic table. And therefore, we know that sulfur should have 16 protons and 16 electrons. And so the electron configuration for sulfur should be 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4. So 1s2, 2s2, 2p6, 3s2, 3p4, which is the correct electron configuration for sulfur. Next, we can write the condensed configuration by recognizing the fact that this part 1s2, 2s2, 2p6 represents the electron configuration for neon, which is the nearest noble gas. And therefore, for the condensed electron configuration, we can simply write neon 3s2, 3p4. And this is the condensed electron configuration for sulfur. Checking our work, we see that sulfur should have 16 electrons, as we mentioned on the previous slide. So adding the electrons, we see that we have 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, 6 electrons in the 3 2p atomic orbitals, 2 electrons in the 3s atomic orbital, and finally 4 electrons in the 3p atomic orbitals. So adding them together gives us a total of 16 electrons, as we expected. In the last part of this question, we are asked to write the partial orbital diagram for sulfur. Looking at the highest energy orbitals, we see that we have 2 electrons in the 3s atomic orbital and 4 electrons in the 3p atomic orbital. So we can place the first electron in the lowest energy orbital, which is the 3s atomic orbital. And so that first electron gets placed in the spin up, or spin plus 1/2 position. The next electron will also go in the 3s atomic orbital, because we have 2 electrons in the 3s atomic orbital, and that electron will go in the spin down, or spin minus 1/2 position. Moving to the p orbitals now, we see that we have 4 electrons in the 3p orbitals. So the first electron will go in the far left p orbital, in the spin up position, and then the second electron in the p orbital will go in the neighboring p orbital, due to Hund's rule of maximum multiplicity. And the third p electron will go in the adjacent p orbital, so we have 3 unpaired electrons, 1 electron in each of the p orbitals, and then the fourth electron will then go in the first p orbital, and this gets placed in the spin down, or spin minus 1/2 position, due to the Pauli exclusion principle, which tells us that no 2 electrons can have the same quantum numbers. You may have noticed that all the groups in the periodic table are numbered consecutively from 1 to 18. These numbers represent the group number. The significance of the group number is that it represents the number of valence electrons for all of the elements in that group. So for example, group 1, the elements in group 1 have 1 valence electron. The elements in group 2 have 2 valence electrons. Once we get to group 13, the number of valence electrons is determined by taking the group number and subtracting 10. So for example, in group 13, we would have 13 minus 10, which gives us 3 valence electrons. Group 14, we would have 4 valence electrons. In group 15, we would have 5 valence electrons, and so on, all the way to group 18, which has 8 valence electrons. The one exception in group 18 is helium, which only has 2 electrons, and so helium only has 2 valence electrons. Valence electrons are defined as the outer shell electrons of an atom. Valence electrons are important because these are the electrons that participate in chemical bonding. As mentioned previously, the group number determines the number of valence electrons for the elements in that group. So for example, group 1 elements have 1 valence electron, and group 17 elements have 7 valence electrons. You'll notice also that the electron configuration is similar for all of the elements in a particular group. So for example, in group 1, which only has 1 valence electron, the electron configuration takes the form ns1, where n represents the period number. And so the 1 valence electron is located in the s orbital in group 1 elements. In group 2 elements, the electron configuration takes the form ns2, where the 2 valence electrons are all located in the ns atomic orbital. Moving down to group 17, we see that the 7 valence electrons in group 17 elements takes the form ns2 and p5. So there are 2 electrons in the s orbital and 5 electrons in the p orbitals, where again n represents the period number. In summary, atomic orbitals fill in order of increasing energy, which leads to valence electron configurations that recur periodically. And this leads to chemical properties that also recur periodically. So in the example we see here, the group 1 metals, or alkali metals, all have 1 valence electron as indicated by the group number. And this valence electron is located in the s subshell. And so all of the metals in group 1 will react with water to produce hydrogen gas, in a reaction such as the one shown below. In this case, we have potassium metal plus water reacting to produce potassium hydroxide plus hydrogen gas, as shown in the photograph here. So as I mentioned, all the group 1 metals will undergo this type of reaction. The difference is that the reactivity of the reaction will increase as we go down the group. In the next example, we have halogens, which are in group 17. And in this case, we have 7 valence electrons, as indicated by the group number, which are located in the s and p subshells. And group 17 elements tend to react with metals to form ionic halides, or salts. The example we have here, sodium metal reacts with chlorine gas to produce sodium chloride. And this type of reaction will occur for all the group 17 elements, and in this case the reactivity increases as we go up the group. Here we distinguish between valence electrons and core electrons. Core electrons, or inner electrons, are defined as electrons that an atom has that are in common with the previous noble gas configuration, and any completed transition series, which means a completed d block. Valence electrons, on the other hand, are defined as electrons that are involved in forming compounds. For main group elements, the valence electrons are the outermost electrons, in other words, the electrons with the highest n value. For example, in phosphorus, which has the electron configuration neon 3s2 3b3, the highest n value in this case is n equals 3, and so phosphorus has 5 valence electrons. 2 of those electrons are in the 3s atomic orbital, and 3 of those electrons are in the 3p atomic orbitals. For transition elements, the valence electrons include the outer electrons, so the ones with the highest n value, and any n-1 d electrons. So for example, for iron, which has the electron configuration argon 4s2 3d6, it would have 8 valence electrons, 4 valence electrons in the 4s atomic orbital and 3 valence electrons in the 3d atomic orbitals.